Morning. Hello. Mhm.
Yes. Yeah. That one is.
All right. Thanks. There's a quiz. Thanks to everyone for taking time out of your busy practice presentation schedule to attend the really important thing. So I wanted to, and I guess I'll do it again, hopefully when is like the practice presentation is just today, right? So tomorrow everyone's free.
No, tomorrow.
Oh, it's tomorrow. Okay. And then it's calc. Okay, great. So this is basically the way I'm thinking about the ESC190. I think I talked about the bigger picture in the beginning of the semester, and then they told you, well, like I can't really explain to you what it's about before I explain to you what it's about. So this is kind of how I think about it. This is also how I think there is a quiz. Hello. This is also how I think about the exam. So principally what ESC190 is about for me is about practicing programming. Everything else is kind of, to me, a little bit of a sideshow. And why? Well, like the only way to really understand what's going on under the hood in the computer is to try to change things, try to debug things. And I think you kind of see that in the lab. It's also the only way to really recognizing what's possible, what's not possible when you're facing with a new problem. And that's the only way, I think, to get to the point where you can also, start thinking about creating new things. So the other reason that we are doing specifically C in ESC190, okay, uh, 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 is you got to be ready for ECE 252 in second year, where you're going to be talking more about what's going on in the hardware, and C is kind of the intermediate step between Python and C. And that's part of why, even though sometimes it's kind of annoying to write things in C when Python is so much easier, we are still working in C because we're preparing to really understand what's going on with the hardware. The other thing that I'm trying to do is to give you some examples of algorithm design. Obviously, like I mentioned, when we started doing dynamic programming, most problems are not necessarily solvable. So what we're showing you is kind of the success stories of here's what people did work out. So for example, people worked out that for some problems, you can use dynamic programming, and that works really well. We'll see the same kind of thing with graph algorithms starting today. It's kind of a little bit like what you see in calculus or linear algebra with theorems. Like, most theorems are really difficult to prove, or they're even false, so you can't prove them because they're false, but sometimes things work out. And one reason to show you theorems is for you to just know what's true, in the same way that one reason to show you dynamic programming is to show you, hey, like this is the kind of thing that can work. The other reason is to kind of inspire you potentially to think about variations on the algorithms that you see. or maybe inventing new algorithms, haven't seen some of the success stories. Sometimes you get to use dynamic programming as well. To be honest, not very often, right? Because usually when faced with a problem, unless it's like an interview setting where or an exam setting where the question is set up specifically so that if you know dynamic programming, you can solve it. Like usually you see a problem, probably dynamic programming is not going to help. But that's fine. The plans for what's left of the semester, which is actually not very little, it's like almost 25%, right? Is finish up a few more examples of data structures and algorithms. I decided to do a little bit fewer data structures and algorithms this year than in previous years, and instead devote a few lectures to one, just telling you in broad strokes how generative AI works. How many people feel like actually like are interested? Like, yeah, okay, good. How many people feel like they have a notion? Okay, yeah, great, I'll tell you. And then we'll talk a little bit about how to use it. So as you saw yesterday and on Monday in the lab, I put kind of an experimental problem. I don't know how well that worked or didn't work because one, those things are always evolving. There's different ways of approaching things. And two, like I said in the handout, actually, some of the time you just plug in the problem and you get the solution right away. So there's not much to it. The challenge with coming up with those problems, which like is impossible because you get a different output every time, is to come up with something that's solvable with the aid of ChatGPT, but is not like directly solvable. And I know that especially with C, a lot of the time, not all of the time, you give it something complicated, it gives you something that doesn't even compile, right? So, and then you're really in trouble. With Python, I think less so. I think probably for a lot of people, if you just ask it, hey, like, give me, a thing that generates the animation with a canon, it'll probably just do it. I think the big problem there would be kind of setting up like, oh, can I actually install the libraries on my computer that read the image, stuff like that. But that's important as well, because if you don't know how to do that, then nothing's going to work. So the other thing, what we've been doing so far is basically writing small programs. Writing software is obviously different. So we'll do, maybe 20 minutes about talking about kind of larger software projects than just, an assignment. And we'll talk a little bit about preparing for PY interviews. So one way that I think about 190 is that unfortunately you do not get a computing course outside of the hardware course in second year in ANXI. So that means that you take 190, then there is second year, and then if you apply for PY, then fall of third year, you get asked questions that are basically like 190 plus. There's never going to be a way for me to actually prepare you for PY interviews in 190. For one thing, just by definition, if everyone in 190 is prepared for the interviews, then they have to come up with 300 jobs for everyone because everyone's prepared. So the way the interviews work is you do kind of have to do stuff outside of class. That's one of the mechanisms by which people get selected is like, hey, like, did you do anything that's kind of on top of standard class material? At the same time, especially for software interviews, which I think about, depending on how you count, like, Robo plus MI plus probably MSF. Currently, it's about, so MI is going down a little bit, Robo is going up a little bit, EC is shooting up, EC also a lot of the time. What you get asked is basically stuff from ESC190 plus. So I cannot possibly prepare you for everything that you might encounter in a job interview, although there is like a standard set of problems that people usually ask. It's just that it's beyond what can possibly be covered in ESC190. But one of my goals in ESC190 is to kind of get you started on that and to point, okay, like, you should be doing stuff that's kind of like that, but more. So we'll talk about that as well. Of course, kind of things are changing. Who knows what, the interviews are going to be in 2 years, but a lot of the time, yeah, like most of what you get asked in software interviews is basically 190. So, okay, that's the plan. So what I want to do now is keep working on the implementation and then do a little bit of algorithms for graphs. So so this is the code from last Thursday. And what we managed to do is we have our is edge, and we have our put edge, and we were about to do remove edge, right? So to do remove edge, what you got to do, so to remind you, we are working with this kind of representation. So for every node, so we have nodes 1, 2, 3. So if 2 and 3 are connected to 1, then 1 has this list of neighbors to 3, right? And then similarly, 2 is just connected to 1, so 1 is just neighbors with 2. And 1 is connected with 3, so 3 is just neighbors with 1. One common confusion is this is implemented in our implementation as a linked list. So it says like 2 arrow 3. That does not mean that 2 is connected to 3. It just means that we store the neighbors, meaning the nodes that have an edge to 1 of 1 in a linked list. So we could have stored it like this as well. The order doesn't matter. Okay, does that make sense? So to remind you, so this code, I posted it before lecture on Piazza. So to remind you, the way we've done it is we started with some number of nodes, and then we just have a list of all the nodes. And for each of the nodes initially, we just append an empty list of neighbors, right? So we have our linked list implementation. And what we did is we just say, okay, this is the empty linked list. We could, of course, have just used a Python list. If you were implementing in C, it would be something like an array list, maybe, right? But here we chose to use a linked list. Like we discussed at the very end of the lecture, the reason is that with a linked list, specifically if you want to insert, that's always O1. If you want to insert just in the beginning, you don't care where. Does that make sense? And that's because the way we insert is we just say insert at position 0. So inserting at position 0 is easy. You just replace the head with the new node. Make sense? So, all right. So we now want to do the remove edge. So to remove an edge, what we need to do is we need to look at the neighbors of I. And similarly, look through the neighbors of J. Just copy and paste this. And remove I from there. Okay. So in order to do that, we actually need the remove functionality in ll.py. So we have our insert, but we didn't have remove. So we'll implement remove here. So so here we'll just say, okay, so we are going to go up until the point where current next is val, but first we'll do the special case where the data is equal to val, in which case we just say, okay, replace the head with head next. That removes the value, right? Otherwise, we start with current being head. And while cur next. And cur next data is not val. So basically, while cur next actually exists and cur next data is not equal to val, we are going to advance cur. So at this point, we found that cur next is the node that we want to remove. How do you remove a node? Easy. You just say. So if it wasn't null, then make it cur next. If it is null, that means that you didn't actually find the value. Yeah. So we are doing like direct. So we are doing directed. So actually, I think what they should. Yeah. So yeah. Yeah. So that was wrong. So we are just doing like a directed edge between I and J. So okay. So now we're saying okay. So to remove the edge. We'll remove J. Okay. I hear a chime from Discord. Okay, there is code on Piazza. It's also from last time. So okay. So all right, okay. So that's done. Does that make sense to everyone? So one thing that's kind of inconvenient is that this graph only has nodes that are like 0, 1, 2, and so on. So that's kind of annoying. What we can do is we can also name the nodes. So how can I do it? One way is I can say I want my nodes to be numbers, but I want to also have them have names. So I'll just have a dictionary that maps names of nodes to the numbers. Okay. So the way I would do it is I would say, okay, initially num node is just going to be nothing. And that's how I'll usually use it. It's just going to be nothing. And then what I'll do is I'll do a dictionary that's initially going to be empty. That's going to be node names. So then I'll have an add node. And if I'm adding the node, what I'm going to do is I'm just going to say, okay, I now have a node and it's going to be node number length of self nodes currently. And it's not going to have any neighbors. I've just added it. And the num nodes is now going to be greater by 1. Okay, so now every time I add a node, I also add a name to that node. Okay. So I might also like to be able to look up nodes by index. So anytime I do this, I'll say this. Okay. So the idea here is now all of my nodes are named, right? So they still are numbers, but I can look up the name that corresponds to the number, and I can look up the number that corresponds to the name. Of course, if I wanted to be kind of particular about it, I would also make sure that if I add a node, then there isn't already a node by that name, stuff like that. But that would just add to the code. So now I'll just do an isEdge name by name. And that would be just the same thing. So I just call isEdge, except I look up the node index by name first. Similarly with putEdge, I'll again do this. So I'll just copy and paste this. So I am using Copilot to give me hints, but I am typing it in, except I copied and pasted this. So this would be putEdge with the same kind of idea. Make sense? Yeah.
So what's the purpose of giving the nodes names if we already have the names?
Yeah. So what's the purpose? So the purpose is that now I can create a graph that's actually easy to use. So here I said like put edge 1, 2, whatever, right? So that's not super convenient. But now what I can do is say I have my, for example, airports graph. And now I want to add a node by name. So let's say, so YYZ is Toronto, right? And then YVR is Vancouver. And I'll add like something, I don't know, like whatever, JFK. And now let's say that I want to have an edge from YYZ to YVR and to JFK, but I don't want to have an edge between JFK and YVR. So I can just do that. Do the other way. So let's say from YVR to YYZ. Then I'll copy and paste this, and I'll have like YYZ to JFK. And I'll have a return flight from Vancouver to Toronto. Okay. And now I've created this graph, and I can refer to the nodes by name instead of having numbers. So what this would represent is something like this. So you have, you know, YYZ, and you have YVR, and you have JFK. and you have an arrow going this way. And you also have an arrow going this way. And you also have an arrow going this way, right? So YVR and YYZ are connected both ways. And then YYZ is also connected to JFK. Makes sense. So, okay. So what we kind of managed to do up to this point is just create this way for us to record something like this graph. Yeah.
Back to the init function for graph.
Yeah. So the way we do it, right, is we kind of decided that internally the nodes are just indices, are just in an array with a list rather that's just indexed. And then if I want to access the node by name, then what I first do is I look up the index that corresponds to the node. Well, we're not really printing anything, right? So like, so here is like the idea. So if I want to know whether this airport is connected to this airport, what I do is I look up the index that corresponds to the airport name 1, and I look up the index that corresponds to the airport name 2, and then I just use my is edge with the indices, right? So this is I and this is J. Yeah. Okay. All right. So that's like that. So now what I want to do is I want to implement something interesting here. So the first thing that you would want to do maybe with a graph is to print it. And unlike with the list where it's just a for loop, with a graph, maybe what you want to do is you want to like walk along the graph and print everything, right? So if you have a graph that's kind of like this, you might like to say, well, like I'll just like start with YVR and then I'll walk to YYZ along this arrow. And then I already was in YVR, so I'll go to JFK. And then that will have printed out the entire graph. Yeah.
Are these edges like they can go both ways? Or
well, so here, yeah, so here it's directed, right? So here I put an edge from YVR to YYZ and also from YYZ to YVR. Yeah, but not with YYZ JFK. Okay, so this is kind of an error. So, okay. So this is what's called the graph traversal problem. So I want to basically list out all the nodes in the graph, and I want to list them out only once for each one of them, right? So basically what I want to do is I want to say, okay, I want to start with 1, and then I want to walk to something, I want to visit 3, I want to visit 2, I want to visit whatever I can here, so not 3, so 8, so 5, then I can go to 4 maybe, and then I'm stuck because I already was at 3, so go back, maybe try 6, already was at 1, so go back, and basically list out everything eventually by walking somehow on the graph. There's several ways of doing it, so here's one. So basically, here's what we're going to do. So we're going to have some data structure, and there can be different data structures there. So we'll call it DS. And the algorithm will be like that. So we'll have DS as the vertices, the nodes that we want to visit but haven't visited yet. So that's going to be stored in DS. The reason we call it data structure is they can be different data structures, and depending on which data structures they are, it's going to work out differently. So here, what we're going to do is we're going to say, okay, initially put in something into DS, and then keep doing this. So if DS is not empty, get me some non-visited vertex from DS and visit it. And then take all the adjacent vertices. So adjacent means means that there is an edge from VJ to them, and add them to the DS. So here's an example. Let's say that DS is a queue. So what this means is we have our queue. So the queue contains all the nodes that we want to visit but haven't visited yet. Okay. So let's say we start with 1. So we are over here. So we visit 1 and we say, okay, add the neighbors of 1, so 3 and 6 to the queue. So we visit 1 and 3 and 6 get added to the queue because they're adjacent to 1. So 3 and 6 is like to be visited. And now we say, okay, what's the next thing I want to visit? Well, I want to visit the first in line in the queue. So I'll visit 3. So 3 is now visited. Okay. So if 3 is visited, we want to add the vertices that are adjacent to 3 to the queue. So what's adjacent to 3 is 2 and 5 and 4. And they are added to the queue. So at this point, 1 and 3 are visited, and all of those guys are waiting around. I take the first guy from the queue. So this is 6, and I visit 6. 6 has neighbors 1 and 5. They are already in the queue, so we don't add stuff to the queue again. And now we get the next in line. So 6 is the next in line to be visited. So 6 is visited. 6's neighbors are 1 and 5 already in the queue. We get the next guy from the queue, that's 2. So 2 is visited, the next guy from the queue, 5, so 5 is visited. Skip 4. Okay. So eventually what we get here is all the nodes, assuming that everything is, if there is a path from the node that we started at to everything, eventually everything will get visited. Yeah. So VI is just like a 1-up, right? So we add some vertex VI to TS as the first step. And then every time here, we get some kind of VJ. So the J changes, so like I could change as well, but like VI happens the once. And then here we get VJ every time for a different J.
So VJ VJ is like VJ's nodes too.
No, so VJ is the next node in line in the queue. Yeah. Do I add? No, so what I do is I look up the neighbors. So if my neighbors are stored in, for example, a linked list, as they are, in the implementation we're talking about, then I'll probably just walk across the walk along the linked list and just add them in the order that they are there. So so those are just so like those are like numbers, but they could they're just nodes, right? So they could be strings, for example. Nodes are in fact named in in our thing. Okay. So all right. So here's kind of like conceptually what's going on here. So conceptually, what I want to do is I want to just like walk along the graph. But as I'm walking along the graph, there's different directions in which it can go, right? So if I start with 1, I can go to 3 or I can go to 6. So I say, okay, like I'll add 3 and 6 to the queue of the stuff to be visited. And then I'll look at the queue and see what's first. So if 3 is first, for example, I'll go to 3 first, but 6 is waiting in the queue. So next time I'll visit 6. Okay. So if you think about it in terms of a queue, so you think about it in terms of anytime there is a neighbor, I put them in the queue. So the first time, so the earlier I see the neighbor, the earlier I'll visit it, right? So what is it going to look like geometrically? So if I start with 1, that means that after 1, I'll visit the neighbors of 1. So I'll visit 3 and 6 in some order. And then I'll visit the neighbors of 3 and the neighbors of 6, right? So one way to think about it is I'm visiting like this part of the graph, so just the 1. And then I'm visiting the stuff that's connected to 1. So I'm visiting kind of this part of the graph. And then I'm visiting this part of the graph, right? So I go kind of layer by layer. Does that make sense to people? Okay, let us implement this. So this is called depth. So this is called breadth for search. Traversal rather. And it's going to take G. And it's going to take start. So what I'll do very quickly is we already did that. So I'll just quickly make a file with a queue and a stack so that they can switch between them. So you don't have to copy it, or you can. Or you can generate it with ChatGPT, you now know how, or we have code somewhere in the course notes as well for that. So one thing that I want to change here is instead of onQ and DQ and push and pop, I want to say add and get so that I can just switch those things around. Right? So, okay. So this is just like the queue that we've done before as well. So, okay. So what am I going to do here? So I'm going to say, all right, we start with start I. And now we say, okay, what's been visited, what's not been visited. So this is initially going to be false, 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 and so on. So now I know what's been visited, what's not been visited, right? And now I'll have my DS, which initially I'll make a cube. And I'll put start I in DS. Okay. So, all right. So now what I want to keep doing is keep getting a node from DS, adding all its neighbors to DS, and visiting the node. Right. And eventually, if I do that, so I keep visiting a node, adding all its neighbors to be visited later. And then again, get me the next one, add all its neighbors, visit them later. So here we have an is empty. Is empty just returns, the length is, or like the items is empty. I'll get something from IDS. And it's possible that it was already visited, in which case I just ignore it and I'll get the next one. Or maybe it wasn't visited, in which case I visit it. So by visit, I mean I print the name and I say that it was visited, right? So here, so this is not super efficient. We do have a linked list, so we can efficiently just go through that linked list and get everything, right? So I'll say current is the head. Done. Okay. So what's the idea again? The idea is I have my DS, in this case Q, and I keep saying I'm gonna go to some node, add all its neighbors to the queue, I'll visit them eventually. And then say, okay, I need to visit the next thing, get me something from the queue, I'll visit it. I visit something, add all its neighbors to the queue to be added later, to be visited later, and repeat. Keep doing that while the queue is not empty. So here, I don't really want to add the same thing twice. So I'll check whether it was already visited. Make sense? So again, kind of so I think like it's a little bit of code. I think the concept is quite simple, right? So the concept is just add a node, I'll visit all the neighbors later, get me a new node from the queue to visit, add all its neighbors, visit them later, get me a new one from the queue to visit, right? Because it's a queue, so queue means the first thing that gets added to it is the first thing that gets out. So that means that if I visit 1 and I add 6 and 3 to the queue, then I'm going to visit 3 and 6 first because they're first in the queue. And then as I visit them, I'll also add their neighbors, which will be visited later because it's a queue, right? So if the neighbors were added later, they will be visited later. So the effect of that is I visit, for example, if I start with this, I visit this one, and then I visit 3 and 6 because they are immediately next to 1. And then I'll visit the neighbors of 3 and 6 in whichever order they were added. So this is kind of why it's called breadth first. So breadth first means I want to, do this layer, and then I want to do this layer, and then I want to do this layer, right? So this is as opposed to depth first, where maybe what I want to do instead is I want to go as far as possible from the initial node as quickly as possible, right? So the alternative is I want to get away from 1. So rather than visit all the neighbors, I'll go to 1 neighbor, and then I'll go like to another neighbor of 3. Yeah, exactly. So if instead of using a queue, you use a stack, that goes the other way, right? So if you're saying I'll start with 1, and then I'll add the neighbors of 1 to the stack. So I'll add 3 and 6 to the stack. And then let's say I add 3 first and then 6. So then I'll get 6. And then I visit 6. I add the neighbor of 6 to the stack. And the next thing that I'll get from the stack is the 5. And then I'll add the neighbors of 5 to the stack. And the next thing I'll get is a neighbor of 5. So if I use a stack in order to keep the pile of things that I haven't visited yet, then the last thing that I add is the first thing that gets out of the stack, which means that I go first to 1, then to the neighbor of 1, to the neighbor of the neighbor of 1, to the neighbor of the neighbor of the neighbor, and so on. So that means that I'm basically getting away from 1 as fast as possible. Eventually, of course, I'll get to anything because I am adding all the neighbors to DS. So eventually I'll get around to everything. Make sense? And the way I did the implementation, it's really easy. So instead of saying ds.queue, you'll just say ds.stack, and that's going to be depth first. Make sense? All right, so why would I care about it? Well, I can print out the nodes in different ways. If you think about the graph as trying to find, trying to say, okay, like I want to explore all the nodes and I want to find the particular node I'm looking for. Sometimes what you want to do is you want to look for stuff that's nearby. Sometimes what you want to do is go far away. I'll do an analogy with that next time. Hey, I will see you tomorrow, assuming Traxxas doesn't get in the way or something. All right, see ya.